back with our final lesson on Riemann sums. This is Riemann sums part 2. And we left off in our last video after deriving the formula for a Riemann sum, which finds the exact area trapped between a function and the x-axis. We're going to actually use the formula now on the function we've been working with throughout this packet. So we're going to find the exact area trapped between the linear function f of x equals x plus 2 and the x-axis from x equals 2 to x equals 10. So we're basically just going to work through the formula we derived here. So let's start with that. So we're going to start with the limit as n approaches infinity of the sum from I equals 1 to n. And now we're going to get specific. F of x sub I and delta x right now are generic and can work for any function and any change in x. We're going to focus on the specifics of our situation. So let's look at f of x sub I. Okay, well, I'm going to call this my side work. We've done side work many times. And underneath my side work, since I'm looking for f of x sub I, it might be a good idea to just recopy down what f of x is. So if f of x is x plus 2, then f of x sub I would just be x sub I plus 2. So I'm going to click and drag this over here to my formula for f of x sub I. So it's going to be x sub I plus 2. Now we're going to multiply that by delta x. So now we've got to get specific with what delta x is. So if you remember from earlier with our rectangle work, to find the change in x, we simply take b minus a, the distance between our a and our b, and we divide that space into n equal subintervals. So for us, in this specific example, we would have 10 minus 2, b minus a, divided by n. Now I'm going to actually let n stay n. When we did 4 rectangles, we let n be 4. When we did 8, we let it be 8. When we did 16, we let it be 16. But I'm going to let n eventually approach infinity, so I want to leave n as n. So my delta x is simply going to be 8 divided by n. So I'm going to carry that up here to delta x. Alright, so I have my f of x sub I here. I have my delta x, which is taking a distance of 8 units between 2 and 10 and splitting it into n equal subintervals. Okay, now the next thing I need to do is figure out what x sub I is. Now, I'm eventually going to give you a formula for how you find x sub I, but the first time we do it, we're going to derive it. So I'm going to go back to my side work. So this was the first part of my side work. This was the second part of my side work. The third part of my side work is going to be to find x sub I in this case. Okay, so let's start with x sub 0. X sub 0 is your initial x value. So for us, in this example, our initial x value is 2. So x sub 0 is 2. Now, to get to the next x value, x sub 1, we simply take our initial x value and add a delta x. Add 8 over n, because our delta x in this example is 8 over n. So if you think about it on the x-axis, let me kind of draw this here. If you think about the x-axis, if you're starting at your x sub 0, which is also your a value, then to kick over to x sub 1, you simply add a delta x. So this puts you at a plus delta x. Okay, to get to x sub 2, okay, that would be adding another delta x. So x sub 2 can be written as your a value plus 2 delta x's. So you're starting at 2, and to that you're adding 2 change in x's. Same, to get to x sub 3, you would add another delta x, or you would take your initial value and add 1, 2, 3 delta x's. So x sub 3 would be your initial value plus 3 of your delta x's, or in this case, 8 divided by n. So we can do like a dot, dot, dot. This will go on and on and on, pushing you through the interval and grabbing. We're going to need to push through so we can grab the heights as we go of our rectangles. Finally, your x sub I is just going to be your initial starting value plus I delta x's, or I times 8 over n. So if I clean that up, x sub I in this example is just going to be 2 plus 8i over n. Now, the formula. We can actually shorten this up so that we don't have to go through this every time. The formula to find x sub I for any given problem is simply this. Your x sub I, let's just kind of highlight this in orange. So your x sub I is just going to be your A value, or your starting point, plus I times your delta x. That's the formula. So first thing you find in your side work, right here, f of x sub I. Second thing you find in your side work, delta x. And the third thing you find in your side work is x sub I, which is your A value from the original starting x plus I times your delta x. This is the third thing you find. Okay, so now we're going to take this x sub I right here, and we're going to feed this back into x sub I right here. So our next step is going to look like this. The limit as n approaches infinity of the sum from I equals 1 to n of 2 plus 8i over n, that's your x sub I, bring down the plus 2, and this is all still times 8 over n. Okay, combine some like terms here. We're going to have the limit as n approaches infinity of the sum from I equals 1 to n. 2 plus 2 is 4, so we have 4 plus 8i over n multiplied by 8 over n. And the next thing I'm going to do is distribute. I'm going to distribute 8 over n to both parts of this binomial. So that will give me the limit as n approaches infinity of the sum from I equals 1 to n of 32 over n plus 64i divided by n squared. Okay. Now, I'm running out of room, so I'm actually going to bring in a separate sheet of paper here, and I'm going to recopy where I am. So I'm going to recopy that last step here. I have the limit as n approaches infinity of the sum from I equals 1 to n of 32 divided by n plus 64i divided by n squared. Okay, now I'm going to use the formula, the sigma formula we derived 2 days ago. Remember the formula that said when you have the sum from I equals 1 to n of a sub I plus b sub I, that you can split those up into 2 different sigmas? So if you look back at that rule, my next step will follow it. So it's going to look like this. The limit as n, actually I was a little high there, let me pull this down. The limit as n approaches infinity of the sum from I equals 1 to n of 32 over n plus, now I'm going to rewrite it, the limit as n approaches infinity of the sum from I equals 1 to n of 64i divided by n squared. Okay, so just split that up into 2 different sigmas, 2 different limits. Now, if you take a look at this right here, this models another sigma formula that we worked on 2 days ago. And what this one models is the sum from I equals 1 to n of a constant. The 32 over n is going to be considered a constant because we're going to add up n of these, which if you have n of these, then you're going to multiply n times 32 over n, and you're just going to be left with 32. So remember how this rule said when you have a constant, you just take n times c, you just multiply those together? So that's what we're going to do. And we can also think of this as a constant because there's no I in it. See how the I is over here in this one, the 64I? This doesn't have an I. So this is going to model a constant right here. So now what we have to drop the sigma is the limit as n approaches infinity of n times 32 over n, which is eventually just going to become the limit as n approaches infinity of 32. And you know, when you do a limit, you just plug it in. Well, once these n's cancel out, once we take these and multiply them, you just have the limit as n approaches infinity of 32. And you try to plug it in, there's no n to plug in, so the answer to this side here is just 32. So we'll be carrying 32 along until we get this right side done. So that one was pretty simple. Now, over here, we are going to use the rule from 2 days ago that said when you have a sum from I equals 1 to n of a constant times a sub I, you are allowed to pull the constant to the front and then rewrite the sum from I equals 1 to n of a sub I. So that's what I'm going to use on this guy. So the constant here in this fraction is the 64 over n squared. So I'm going to pull 64 over n squared to the front of the sigma and keep the I tucked inside. It's going to look like that. All right, now I'm going to bring this plus sign down and I'm going to continue on because I have more steps to do here on the right. Okay, so the next thing I'm going to do is take this part of my process here. There was a rule we learned that I asked you to memorize that said the sum from I equals 1 to n of I is equal to n times n plus 1 all over 2. So I'm going to replace this entire expression with the right side, n times n plus 1 over 2, which is going to make all my sigmas go away. So now I have the limit as n approaches infinity of 64 over n squared times n plus 1 all over 2. And really, all that's left is a limit, which was that's taking us all the way back to chapter 2. So I just have to clean it up with a little bit of algebra. So I'll bring this 32 down, recopy my limit. I am going to, let's see, I'll probably take n and distribute it in here. And I'll make this 64 over n squared times n squared plus n all over 2. And then I'll multiply 64 through the top, and on the bottom I'll multiply n squared times 2. So my next step, just using algebra, is going to be 64n squared plus 64n all over 2n squared. Okay? Now, if I were to plug infinity in here right now, I would end up getting infinity over infinity, which is undefined. And we know from chapter 2 that what we do with limits at infinity is we divide each term by the highest power of n in the denominator, so it's going to look like this. 64n squared over n squared plus 64n over n squared all over 2n squared over n squared. Then we reduce. So I have 32 plus the limit as n approaches infinity. Here, these are going to cancel, giving me 64. Here, I'm going to reduce these n's to give me 64 over n. And on the bottom, I just have the 2. Now, when I plug my infinity back in, I get 32 plus 64 plus 64 over infinity all over 2. This guy right here is going to go to 0. So I've got 32 plus 64 divided by 2, which is 32, giving me a final exact area of 64 units squared. Now if I go backwards here, if you remember the other day in one of the other videos, we found the area trapped between the linear function and the x-axis to be right here, 64. Using area of a trapezoid geometry. Now, using Riemann sums, we tackled it a completely different way. using the formula for Riemann, and we got the same answer, 64 units squared. So your homework tonight is going to be to continue on in the packet and use Riemann sums to do numbers 1, 2, and 3. So the best thing to do is graph them, graph these linear functions on the given interval, take a look at it, use geometry first if you can, just to know what your final answer is. I've got some helpful tips right here. The formula to find delta x is b minus a over n. There's that formula we derived for x sub I. It's a plus I times delta x. So hopefully you'll have success with this. Good luck.